Hello friends, this is the classic problem of Irodov's 3.146. Here, this is a semicircular parallel plate capacitor of radius capital R, which has a semicircular dielectric slab of same shape within it. The thickness of this slab is small d. That is, the separation between these two plates is small d. A constant potential of value capital V is maintained between these two plates. There is a smooth hinge at the center so that the semicircular dielectric slab can be easily rotated. Now, whenever we try to rotate this dielectric slab, this capacitor applies a opposing force just to oppose this rotation. Why this capacitor behaves like this? Actually, the capacitor is its equilibrium energy. So whenever we try to change its energy, it opposes. Actually, whenever we try to rotate this dielectric slab, its energy changes. So it doesn't like, the capacitor doesn't like to change its energy. For this, it applies a opposing torque to oppose this rotation. We have to find out this torque in this problem. We solve this problem by energy method. Now we know that the energy density of electric field has the form like this: small u is equal to half epsilon naught square. That is, energy of electric field per unit volume has the value half epsilon naught square, where is the electric field intensity. Here, constant electric field fills the region within these two plates, and we know that V is equal to ED, that is, V potential difference is the work done against this electric field. So V is equal to E into small d. So we have E is equal to V by d. Now, whenever this dielectric slab is rotated, the space between these two plates, the volume of the space between these two plates changes. Let from this position, that is, when the dielectric slab is at angular position phi, the slab is further rotated by a very small angular displacement d phi. Then, due to this elementary further rotation, the change in volume within these plates would be the volume of this portion. When d phi tends to 0, this arc length r d phi would be perpendicular to this r. So the volume of this elementary portion would be area of this upper face into multiplied by this thickness small d. Area of this upper face would be half r into r d phi, and the thickness is d. So this would be the change in volume due to elementary rotation d phi. Due to this change in volume, the corresponding change in energy would be like this: half epsilon minus epsilon naught square into this term, that is, this is the change in volume. where epsilon is the permittivity of this dielectric slab. We know that epsilon is equal to epsilon naught into k. K is the dielectric constant. Just put these two values, that is the elementary change that is change in volume, elementary change in volume here, and the value of capital E from here. We readily get the change in energy. But we know that the change in energy due to torque applied, here tau is the torque, is nothing but d tau d phi is equal to du. So just equate this, by comparing these two equation, we readily get the applied torque as this one. Thanks.